When we talk about human achievement and exploration, the conversation usually focuses on reaching the highest points. Thousands of people have successfully summited Mount Everest. It's seen as the ultimate vertical challenge.
And yeah, rightfully so. It's an incredible feat. But when you compare that, thousand-strong club to the group who have visited the deepest known point on Earth, the Challenger Deep, well, the perspective shifts entirely.
How many are we talking about?
We are talking about fewer people who have gone to the bottom of the Mariana Trench than have actually walked on the surface of the moon.
Wow. That immediately establishes the scale of the challenge, doesn't it? And that scale, both geological and technological, is exactly what we are diving into today.
Hmm.
We are taking you on a deep dive into the Challenger Deep, exploring how it formed, the frankly unbelievable technology required to measure and reach it, and finally, maybe surprisingly, the human legacy waiting at the bottom.
And just to give you a visceral sense of the depth we're analyzing, if you took Mount Everest, the tallest mountain on the planet, and you could somehow place it in the Challenger Deep,
Yeah.
its peak would still sit more than a mile beneath the surface of the water.
A mile of water above Everest's peak. That's staggering.
That's the kind of distance we're covering.
Okay, let's unpack this. Starting with the geology. How does a place like this even form? It must involve some pretty powerful geological events.
Oh, absolutely. The Challenger Deep is the deepest part of the Mariana Trench itself. And the trench is this colossal crescent-shaped feature in the western Pacific Ocean, just east of the Philippines. It's like a scar stretching over 1,500 miles long.
Right, I've seen maps. It's huge. And its profound depth is directly related to the movement of our planet's crust, isn't it? It's not just a random hole. It's something called a convergent boundary.
Precisely. It's where the dense oceanic crust of the Pacific Plate collides with and then slides beneath the less dense Philippine Sea Plate. This plunging action is called subduction, and it's that resulting downward drag that creates the immense depth of the trench itself.
This sounds, well, pretty catastrophic. But you've mentioned before that this subduction isn't just a local thing. It's part of a bigger global mechanism that keeps Earth sort of balanced, like a giant conveyor belt.
It is the ultimate balancing act, really. You have new crust being created at divergent margins, the mid-ocean ridges where the seafloor spreads.
Right, making new rock.
Exactly. But the planet isn't getting bigger, so that crust must be recycled somewhere else. Subduction zones, especially these really deep ones like the Mariana Trench, are the planet's way of reducing the crust's surface area by plunging that old material back down into the mantle.
So it keeps everything in check.
It's a critical part of the whole global tectonic system. And, importantly, its movement is why these specific plate boundaries generate the largest earthquakes and, consequently, the biggest tsunamis we see globally.
Okay, that makes sense. Now, what's fascinating, according to some recent research from the Southern Mariana Trench, is the critical role water plays in all this recycling. We tend to think of plate tectonics as just solid rock grinding against rock, but water seems key here.
It is absolutely key, and it really changes our understanding of how crust gets recycled deep inside the Earth. Researchers looked at the Pacific Plate in this zone, and it's ancient-like, 145 to 155 million years old.
Wow!
And as this massive old plate bends sharply downwards to subduct, it actually develops deep fissures. These are called bending-related normal faults, and sometimes the vertical displacement, the throw, can be up to 450 meters.
450 meters, that's huge. So if I'm picturing this right, these faults aren't just small cracks, they're massive pathways channeling seawater deep into the Earth's interior.
That's exactly the right way to think about it. All that water rushes into these conduits, and it creates high levels of hydration in the surrounding rock. It's a process we call serpentinization.
Serpentinization.
Okay. And what's truly insightful is that the Southern Mariana Trench is considered an end-member example of this process. That just means it transports a really substantial, maybe disproportionate amount of water deep into the mantle compared to other subduction zones.
Okay, but why does that matter beyond just the local geology there? What's the bigger consequence of sinking all that water deep into the planet?
Well, it fundamentally influences tectonic processes on a much larger scale. When you introduce water into the mantle, you change its rheology, basically how the rock behaves under heat and pressure.
Ah, okay.
This absorbed water can act like a lubricant for the system. It can potentially influence where and how much the plate melts, how large the resulting volcanism is above the subduction zone, and ultimately it affects the Earth's deep water cycle, how much water stays locked in the mantle versus how much eventually gets cycled back out. It helps us map the planet's internal water budget, essentially.
That's incredible. The deepest part of the ocean is actually teaching us about the deepest parts of the Earth itself. But I imagine measuring something so deep, so remote, so chaotic, that must be incredibly challenging. Let's shift gears to mapping. How did we even figure out how deep it was?
Well, the initial efforts were almost comical by today's standards, but state-of-the-art then. In 1875, the British Royal Navy's Challenger expedition,
The original Challenger.
the original one, yeah, they basically just dropped a weighted rope over the side and recorded a depth of about 8,184 meters. Simple, but groundbreaking for the time.
It's just a rope.
Pretty much. Then in 1951, another British survey vessel, Challenger 2, did a more detailed survey using echo sounding and actually provided the name Challenger Deep that we use today.
Okay, so echo sounding was the next step. But today, we rely on much more sophisticated modern bathymetry, primarily using something called multi-beam echo sounders, or MBES.
Exactly. This is a huge leap forward from just a single echo sounder. MBES systems send out multiple simultaneous acoustic pulses pings in a fan shape beneath the ship.
Like spreading the sound out.
Right. By precisely timing the echo return from numerous points across that fan, they create a wide swath of depth data with each pass, not just a single point directly below the ship.
Ah, so you get much better coverage.
Much better. And this technology delivered our current most precise measurement for the Challenger Deep. 10,994 meters plus or minus 40 meters. That was recorded back in a 2010 multi-beam sonar survey.
Okay, 10,994 meters plus or minus 40. That margin of error, 40 meters, brings us to a core question I think you, the listener, probably have. Can scientists definitively guarantee that the Challenger Deep is the absolute deepest spot on the entire planet?
That's where we have to be careful. We have mapped all the major trenches globally. Those are the most likely places for extreme depths, obviously.
Makes sense.
But the resolution of these maps is not uniform. The surveys are often limited to the ship tracks as they crisscross the area. Think of it like mowing a huge lawn with a standard mower. You'll cover most of it, but there are going to be strips left between the passes.
So if a deeper, maybe smaller hole exists in one of those unmapped gaps between the ship tracks, we just wouldn't know about it.
Exactly. And even in the areas we have surveyed with multibeam, the resolution itself has limits. The smallest distinct feature we might be able to resolve on the seafloor might still be, say, 600 feet across. A narrower, deeper feature could potentially be missed, averaged out in the data.
Right.
So while Challenger Deep is currently the undisputed champion at roughly 36,000 feet deep, you have other contenders like the Tonga Trench, which is over 34,000 feet deep. They're close. We know the deepest known spot, but we can't guarantee we found the absolute deepest point possible. The search isn't completely exhausted.
Finding the deepest spot, known or maybe unknown, requires surviving physics that are just utterly unforgiving. Let's talk about the incredible technology needed to get down there. We're talking pressures up to 20,000 psi. What does that even feel like?
It's hard to grasp. It's like having maybe 50 fully loaded jumbo jets stacked on top of a small car. That level of pressure demands absolute perfection in design and materials.
Right. No room for error.
None. We can look at the DSV limiting factor. That's the submersible used by Victor Vescovo for his historic 5 Deeps expedition, reaching the deepest point in all 5 oceans.
Okay, what makes it special?
The core is the pressure hull. It's a sphere made of grade 5 titanium. Titanium is used for its incredible strength-to-weight ratio, and this sphere is machined to an astonishing 99.933% perfect spherical shape.
Why so perfectly round?
That precision is absolutely vital. Any tiny imperfection, any flat spot or deviation becomes a weak point where that colossal pressure would concentrate and instantly crush the vessel. It's certified for 11,000 meters, but tested even beyond that to 14,000 meters, just to be safe.
Incredible engineering. And the limiting factor isn't the only extreme machine built for this, right? James Cameron's Deep-Sea Challenger had a very different design.
Yeah, Cameron's sub was unique. It was oriented vertically, designed for rapid descent and ascent. And they faced a huge materials challenge. Standard buoyant materials, phones used to help subsurface, simply failed under Mariana Trench pressures. They'd crack or implode.
So what did they do?
They had to invent and patent a completely new solution called isofloat syntactic foam. This stuff uses tiny hollow glass microspheres suspended in an epoxy resin. It gave them about twice the tensile strength of previous deep ocean foams. The success of the dive literally depended on creating a material that was light enough to provide buoyancy, but strong enough not to get crushed.
Kind of amazing. And just getting down is one thing. Getting back up safely relies on something pretty simple sounding but absolutely critical, dropping weights. And that needs multiple safety backups.
Oh, redundancy is everything at those depths.
Yeah.
You cannot afford a single point of failure for ascent. They use over 1,000 pounds of steel dive weights, held onto the sub by electromagnets.
Okay, so if the main power fails,
The magnets switch off, the weights drop automatically. That's fail-safe number 1.
good start. What else?
If that somehow fails, layer 2. The surface team can send a specific acoustic command, like a sound signal, telling a backup system to release the weights. Layer 3. There's a galvanic timed release wire. It's designed to corrode in seawater after a set number of hours, say 12 or 14 hours. If nothing else works, it just dissolves and releases the weights.
A ticking clock backup.
Exactly. And finally, layer 4. The pilot inside has a manually activated system, often called a frangible bolt, to physically break the weight assembly free. 4 separate ways to ensure they can get back to the surface. You absolutely don't want to get stranded.
No kidding. Now, speaking of activation and commands from the surface, communication itself in the deep ocean sounds fundamentally difficult. It's not like space where radio waves travel easily.
No, it's a completely different problem.
Yeah.
Water is very effective at absorbing radio waves, so they just don't work for long distances underwater. That forces us to use acoustic waves, sound waves instead.
Okay, sound travels through water.
It does, but it's slow. For just a 1.5-kilometer distance, you're looking at about a 2-second round trip time for a signal. That slow speed translates into extremely low data rates. You're talking kilobits per second, maybe even just bytes per second.
So like sending a text message on a dial-up modem from the 80s?
That's a pretty good analogy, yeah. Trying to have a meaningful real-time conversation or send complex data is incredibly challenging.
But there has been some clever innovation here, apparently inspired by the animal kingdom.
Yes, engineers have actually turned to dolphin biomimetics. They use sophisticated sound signals called chirps. These are frequency-modulated signals. The pitch changes over the duration of the pulse.
Why chirps?
These complex pulses are much easier for the receiving equipment to detect against background ocean noise. And systems like ultra-short baseline, or USBL, use these acoustic pulses to achieve 2 crucial things at once. They provide precise location tracking for the submersible, like an underwater GPS, and they can carry small amounts of data, like text messages or system status updates. It merges navigation and basic communication.
Very clever. So the technological triumph of subs like the Limiting Factor and its support team has allowed us not only to study geology and marine biology down there, but also to achieve some pretty remarkable non-scientific feats, like discovering shipwrecks.
Absolutely. The Limiting Factor team, led by Vescovo and Caladan Oceanic, set the record for the deepest identified shipwreck ever found. They located the USS Samuel B. Roberts, a U.S. Navy destroyer escort, sunk in WWII at an incredible depth of 6,865 meters.
Wow.
And they also surveyed another famous wreck, the USS Johnston, nearby at 6,469 meters. Beyond that, these expeditions have discovered completely new species, weird and wonderful creatures adapted to the Hadal Zone, like unique types of snailfish and bizarre spoonworms. It really demonstrates the unique biological environment down there.
It really is a spectacular display of human ingenuity, exploration, scientific discovery. But here's the pivot and maybe the profound paradox of this whole deep dive we're doing. After all that effort, all that titanium, all that advanced tech,
Right.
what did Victor Vescovo actually report finding on his second dive into the Challenger Deep itself?
Yeah, this is the sobering part. He reported finding some sort of plastic waste.
Plastic at the very bottom. Plastic. And unfortunately, this anecdotal evidence is strongly supported by scientific research, focusing specifically on the southern Mariana Trench. And to understand the scale of this problem, we need to define the area, the Hadal Zone. That's the technical term for the deepest oceanic region, anything below 6,000 meters.
Okay, the Hadal Zone. And the studies there suggest this incredibly remote area is not pristine.
Far, far from it. Studies analyzing water samples from the Hadal bottom waters found microplastic abundances ranging from about 2 pieces up to maybe 13 or 14 pieces per liter.
How does that compare to elsewhere?
Well, that's roughly 4 times higher than the concentration found in typical open ocean subsurface water further up. But the really shocking numbers come from the sediments.
The mud at the bottom.
Exactly. Microplastic abundances in the Hadal sediments themselves range from 200 to an astonishing 2,200 pieces per liter.
2,000 pieces per liter. That concentration is, that sounds incredibly high.
Yeah.
It is. It's comparable to the levels you find in heavily polluted coastal areas and estuaries, places like the mouth of the Yanks River or near major urban centers. We're talking about the most remote, inaccessible place on the planet, having sediment contamination levels similar to some of the most polluted shallow waters near big cities.
That is just deeply disturbing. It really speaks to the ubiquity of our waste, doesn't it? How does this plastic even get all the way down there? Does it just sink?
Well, several factors contribute. First, yes, many common plastics, the polymers like polyethylene and polypropylene often found down there, are naturally negatively buoyant in seawater, meaning they will sink eventually on their own.
Okay, so they sink, but is the process sped up somehow? It seems like a long way down for tiny fragments to just drift.
Exactly. The sinking process is greatly enhanced.
Hmm.
These microplastics don't just sink in isolation. They become colonized by microorganisms, bacteria and algae, form biofilms on them, or they adhere to other sinking organic debris and plankton, stuff we sometimes call marine snow.
So they essentially hitch a ride down.
Pretty much. They become part of that natural rain of organic matter falling into the abyss. And critically, the very shape of the trench plays a role. That narrow V-shaped topography acts like a giant funnel.
Ah, concentrating everything.
Precisely. It enhances the downslope movement, the flux of these sinking particles, effectively channeling them towards the deepest point. It almost guarantees that debris reaching the trench area will eventually end up concentrated at the bottom.
So the very geological forces that created this immense, unique deep sea feature are now actively helping to concentrate our plastic waste in it. It's acting like the planet's deepest garbage sink.
That is the tragic, unavoidable conclusion, it seems. The Haddle Zone, far from being pristine, is likely one of the largest sinks for microplastic debris on Earth. And this poses a potentially devastating and, frankly, unpredictable impact on a unique, fragile ecosystem that we've only just begun to study and understand.
It's quite a sobering thought. We began this deep dive admiring the technological genius required to navigate and survive the crushing pressure of the Challenger Deep. And we end by facing the environmental reality that our most common ubiquitous pollution actually beat us there.
Yeah.
We've demonstrated we can build these incredible machines to withstand 20,000 psi, yet we apparently can't stop our plastic bags and bottles from breaking down and reaching that exact same depth.
And this realization creates a massive challenge for how we manage the deep sea globally. The paradox isn't just about the pollution itself, it's also about managing increasing human pressures in general. Things like the potential for deep-sea mining for valuable minerals or oil and gas extraction moving into deeper waters.
Activities in a biome where, as you say, our knowledge is still so limited.
Exactly. We've gained the ability to map and physically reach these incredible depths, but a fundamental understanding of the Hadal ecosystem, how it functions, what lives there, and how we'll react to disturbance. Well, that understanding is lagging severely behind our industrial capabilities to exploit it.
And that links directly back to the mapping gaps we talked about earlier, doesn't it? If we can't even definitively say we found the absolute deepest spots or map every square inch of these massive trenches, how can we possibly regulate activity effectively down there?
That really raises the most pressing question, perhaps for you, the listener, to consider. We have international agreements and policy recommendations starting to emerge, things like establishing standardized methods for environmental impact assessments in the deep sea, or the global goal of protecting 30% of the ocean by 2030.
Important goals.
Very important. But given the sheer scale of the deep ocean, the known threats, the powerful economic drivers pushing for exploitation, and crucially, these profound knowledge gaps about the Haddle Zone, how quickly can we realistically implement those vital protections? Can we do it before the damage to these unique ecosystems becomes widespread and potentially irreversible? That knowledge gap and the urgent race to fill it is perhaps the next great deep dive humanity needs to undertake.